Okay, welcome back. Before I introduce the speaker, I want to talk about how we've shifted our format for the keynote talks. Instead of having the keynote speaker have to bear the brunt of sustaining the entire discussion, what we're going to do is after the talk, we're going to have you enter questions and potential discussion topics into Slack on the Slack channel for this week. The speaker can then answer the questions, asynchronously, get to all the questions you might have about the talk itself, but you may also add potential discussion topics into that channel. So about an hour from now, we will convene to have a panel discussion where we have other people you might want to bounce questions off of, and they'll be leading the discussion. So that's how we're going to run it, so that we have a little more diversity of ideas involved in the panel. The next speaker, I've been following her scientific career for over 35 years very closely. It's Donahue, and she'll be giving us the part 2 of how do gaseous halos depend on halo mass. I'm going to stop my screen share and ask her to start hers for the talk.
All right, now I'm not. Everything's turned on. It looks like it's working. The Slack idea is interesting. I'm going to have to turn on my Slack after I stop speaking because I turned it off because it was ringing off the hook because I'm in another meeting at the AAS right now. This week is the AAS. I'm the past president, and the current president was stuck in the power outage in Seattle yesterday. And so things got kind of hectic, and I'm still not sure if she's back online yet. So, but other people are handling that now, and so now I'm going to be here. So I've been asked today to talk about gaseous halos and how they depend on halo mass, and specifically, I've been asked to talk about how highest mass halos depend, how the gas in the highest mass halos depend on their mass. And by high mass, I think this group would consider a few times 10 to the 13 solar masses to be fairly high mass. What I would consider a pretty high mass would be another order of magnitude higher than that. Because when you get down to 10 to the 13 solar masses, those gaseous halos get hard to see. And when I'm talking about seeing it, I'm talking about seeing the gaseous halos in the X-rays. So here is a picture of a single cluster of galaxies. It's Abell 383. It has a fairly spectacular lensing system, which you see here in the Hubble Space Telescope picture on the left. There's lensed images of background galaxies. You can see those in the blue and also these orange extended loops. The distortions of that image allow us to measure the distribution of matter in the center of clusters of galaxies, and the statistical distortion of background galaxies can be leveraged to measure the distribution of matter even at much larger radii, a technique known as weak lensing. And on the right-hand side is that same cluster of galaxies as seen with the Chandra X-ray telescope. And there what you're seeing is the gaseous halo in this cluster. It's smoother. There's some lumpiness to it because of possible feedback effects, but when it comes to approximating the distribution of stuff in that halo, that first spherical approximation turns out to be not too terrible. I'd like to make a segue from Xiaowen's very nice talk. And that segue includes the role of feedback in making these halos look the way they do. Xiaowen mentioned how supernova and AGN feedback may suppress the baryonic mass function from what you'd expect if baryons simply follow the dark matter. And she mentioned that AGN feedback may be what suppresses the mass function at the high mass end. And the one comment I'd add is there's another factor that suppresses that, and that's simply that cosmological infall of matter shocks the gas to sufficiently high temperatures that it doesn't easily cool. And so cosmological accretion can also set that, becomes quite important at setting that scale at high masses, and that the long cooling times prevents the gas from condensing into to ever more massive galaxies. The other thing is that galaxy velocities get sufficiently high that you don't simply take a cluster of galaxies. If it was completely dominated by a single galaxy, would be kind of what you'd expect if you just expect galaxies to get bigger with their halo masses. That can't happen in a cluster of galaxies because the galaxy velocities are too high. So you don't merge all the satellite galaxies into a single halo. So feedback is important in setting the conditions in the gas halo, and feedback is critical in understanding why gas halos are harder to see than what you'd expect from simple infall ideas, but it's not the only thing going on. So I just wanted to make that point. So measuring cluster halo masses is it's a huge industry. There are many techniques for measuring the mass of a cluster halo. I'm going to contrast that to how tricky it is to exactly measuring the halo mass of a galaxy. Because we have these multiple techniques. So I had mentioned gravitational lensing. This is considered the gold standard mass. It's considered unbiased. It's considered fairly reliable. It's difficult, but the techniques have improved that the access to wide field, large telescope imaging, such as Subaru and the dark energy cam in the south, have enabled some extraordinary efforts from the ground. Space telescope is pretty good for more distant clusters of galaxies because it can measure the shear distortions of a higher density of background galaxies, as you saw from that first image I showed. But it's limited to usually the cores of clusters of galaxies, and getting these big weak lensing data sets have required large format cameras on the ground. Coming up, though, we're going to be looking at space-based lensing that is going to really transform this field from Euclid and from the Nancy Roman telescope. And I'll mention that at the end of the talk again. Traditionally, cluster masses have been measured with by tracking galaxy orbits, measuring the dispersion, their caustics, their phase space, and checkout works by Biviano and Capasso for updates on that. Other mass surrogates, it turns out the X-ray gas mass is a pretty good surrogate for the total mass. Outside of, if you measure the gas mass to enclosed radii outside of about 0.5 megaparsec, the gas mass is about 1/8 of the lensing mass at about R500. I did that with a study using CLASH clusters. CLASH was a sample of 25 clusters that was studied with the Hubble Space Telescope, and then it attracted a lot of ancillary data. And this has been measured for other cluster samples. And another traditional way of measuring cluster halo mass is using the assumption of near hydrostatic equilibrium and you use the pressure profile as measured in the gas density to infer the gravitational potential gradient and calculate the enclosed mass. And this method does not explicitly account for possible non-thermal pressure, that is pressure support from bulk motions or turbulence, but it's been calibrated, and the variations in the sort of the total masses that you get from this analysis compared to, say, weak lensing masses is typically about, the gas masses. The hydrostatic mass inferred from files is about 80% that of the weak lensing mass. And so that's something that could be calibrated out in principle. And so this is a tough business. I was in it for a while. I have to admit, I had to step away and do other things for a few years. But the challenge is, one is because the mass is distributed, you have to be very specific about radius out to which you're measuring, and this can make the literature going back and figuring out what other people do rather challenging sometimes. And I'll refer you to Mark Voigt's tutorial from yesterday. The virial mass is hard to measure, so you need to define a contrast, and usually this is, in terms of like 500 times the ambient critical density, although some workers use the contrast with the mean density as opposed to the critical density. And it's important to keep track of the distinctions. There are systematics in these measurements, backgrounds and foregrounds, both for weak lensing, X-rays. These are all things that are technical, and you have to get your hands dirty in it if you want to do a good job in this business. And then there's observational biases. So I'll bring up Malmquist bias, which is the bias you get from selecting a sample by its flux. And so you tend to include the brightest examples of the underlying, say, volume limited set. And that can skew your answer. And another one, which is particularly important, I think, for clusters and mass measurements, is a bias that's called Eddington bias. And Eddington bias is a shorthand jargon term for that bias that you get when the underlying population is deeply dependent on the parameter you're trying to measure. So the number density of clusters drops like a rock, exponential with mass. So the higher the mass, the more rare a cluster is. And if your mass measurement has an uncertainty, which it always does, then your lower mass objects scatter into your higher mass bins. And so you have to take into account of all these biases when you're fitting a mass scaling relation. And that's why sometimes you see a mass scaling relation where you see the data and then the fit doesn't seem to go through the data. So if you see a mass scaling relation like of mass versus luminosity and the line doesn't go through the data, that's the reason. They're accounting for the bias that you're only seeing the brightest examples. And this is, so you have to simultaneously fit for the underlying distribution and the mass scaling relation, which is usually what the thing is plotted. So, so this has cosmological implications because cluster mass is one of the things that you can predict from cosmological principles, and so it's gotten a lot of attention. For example, there is still, as far as I understand, a continuing controversy and tension between the, for example, the Planck cosmological parameters that allow you to predict the number density of clusters as a function of mass, and the number and masses of the clusters that Planck actually sees. And so the gray line on this plot where 1 minus b is just the ratio of the Selfsimilar mass divided by the weak lensing mass. The gray bar at the bottom of this plot is the bar that the measurements would have to be biased to 60%. That the Selfsimilar mass would have to be 60% of the weak lensing mass, a pretty severe bias, in order to bring the cosmological parameter-based prediction of the number density of clusters into agreement with the number density of clusters and masses that were estimated for the Planck survey. And the Planck analysis assumes something more like 0.8, so that there's a 20% shortfall in the estimated from this Selfsimilar effect, which is based on the integral of the gas pressure integrated through a cluster that gives you a signal that you would see against the cosmic microwave background. And so you see plotted here from a 2020 review from Keiichi Umetsu, a number of different estimates for what this bias actually is based on weak lensing measurements of clusters. You see the clash point at a typical mass for that sample is 6 × 10⁻14 solar masses. There's some other, weighing the giants is one of the first studies. The CCCP clusters for the masses is the purple points, and some other recent analyses are also plotted there. So you see that there is some disagreement about what the bias is. I would say most would say it's somewhere between 25% or 20% or so, but there's some uncertainty and some debate. None of the measurements really reach the point of resolving the Planck conflict, and that's why it's still kind of a conflict. However, the take-home point is that actually these mass measurements turn out to be better than expected. From my point of view, from the cosmologist's point of view, it's like, oh my goodness, we have this, this difference. But from my point of view, and I want to understand clusters and how gas behaves in gravitational potentials, this is pretty good. And so why is this better than expected? And yes, it's better than 10 to 20% mass estimates is better than expected, because just go back to the literature from the 90s. I mean, there was sometimes factors of 3 and 4 discrepancies with the earlier measurements, and it just turned out that a lot of people, they weren't measuring out far enough, and the measurements weren't quite accurate yet. So one reason cluster mass measurements are pretty good, in pretty good shape, is because they're decent fair samples of the universe, and they're not quite as biased as some may have hoped back in the 90s when omega matter was supposed to be 1, and they were trying to explain why clusters weren't giving them that answer. But it turned out clusters were pretty fair samples of the universe. Omega matter was not one. Hydrostatic equilibrium, while it's clearly not the case for clusters that are merging and so forth, it's not a bad 0th order basis on which to start analyzing clusters and estimating their masses, because gravity is such an important process in setting the scales and the energy scales in the cluster. The bias was never expected to be 0%. It's going to be larger where non-thermal processes provide pressure support over gas pressure, and it's going to be smaller where those processes are negligible, and I'll show you some examples of that in a couple slides. So let's go way back and talk a little bit about self-similar expectations. Some of these slides will have a line showing what these expectations are, and I just wanted to walk you through what's self-similar is and why we bothered to talk about it, even though it's obviously not correctly representing what happens. One of the reasons I think we do this is because sometimes our models really aren't expected to determine what happens, but it provides a baseline so we can have a conversation about when the observations deviate from self-similar. You know, the question is why, and often the answer is because feedback and other processes are important. So self-similar just starts out with a gravitational collapse in an expanding universe that's described by a Hubble constant that varies with redshift based on the contents of the universe. So it generates, you know, scale-free. There's no scale, and that's where the term self-similar comes from, parallel scaling relations. You can write down on the back of an envelope what you'd expect for the mass inside a contrast radius based on some number like 200 or 500 times the critical density. Delta, replace that delta with a 200 or 500 to give typical mass scales that we use. And you can calculate the expected circular velocity proportional to m over r. So v cubed is proportional to the mass times the Hubble constant, which is proportional to t squared, and you get that the X-ray temperature you'd expect is proportional to mass times this Hubble parameter to the 2/3 power. This self-similar expectation also allows us to scale observed properties of clusters at different redshift to kind of put them on the same footing with respect to each other. So you'll see self-similar scaling, even though self-similar might not apply. Then you just take that a little further, you know, as Kaiser did in 1986, and you know, estimate what the expectations are for the hot gas. And the hot gas in a cluster is going to be proportional to the gas density squared because it's a collisional process. Thermal Bremsstrahlung and emission line production is a collisional process proportional to r cubed. And then lambda, which here is a term we use for the cooling function, which is the function of temperature, metallicity of the gas, which I'm throw here as a capital Z. I'm not going to talk about metallicity anymore. And depending on the bandpass, this lambda, the X-ray bandpass you're looking at the gas in, this lambda maybe have a strong dependence on temperature or a fairly weak one. So if you're just looking at the lowest energy or soft X-rays, for example, from ROSAT, this cooling function it's insensitive to temperature. And if you're making a bolometric estimate based on a broader bandpass, the lambda is proportional to t to the 1/2. So you can write down then expressions for the relationship between X-ray luminosity and mass, depending on whether your X-ray luminosity is being measured in, say, the ROSAT bandpass or a bolometric bandpass. And similar expressions can be done for SZ, the Y parameter in SZ, or the gas, which is going to be proportional to the gas mass times the temperature. So you have different expectations from self-similarity for different parameter scaling with mass. And here's an example of a paper, a very nice paper written by Sarah Mulroy for the Locus analysis. It's based on 41 clusters between a redshift of 0.15 and 0.3. This work is notable because there's a very well-defined X-ray selection function that they take into account, and they drive scaling, a very rich ancillary data set. So they have fit scaling functions to Xray, Sinyaev, Zeldovich, and optical mass estimators. They also have weak lensing masses for all of these clusters. So these estimators don't depend on the assumption of hydrostatic equilibrium. They find 1 to 2 sigma discrepancies with self-similar expectations. If you look at their table 5, it's a massive list of comparisons to between their fits and self-similarity. I note that their analysis assumes that this weak lensing mass is an unbiased tracer of mass. And I've shown a couple of their plots. One is a temperature weak lensing mass plot on the left, and the plot on the right is a gas mass versus weak lensing mass. You see this E of Z, that's just the dependence of redshift on the Hubble parameter, where you would write the Hubble parameter H of Z is equal to H naught times E of Z. So that takes out any scaling that's simply owing to the different values of the critical density at the redshift of the cluster. And the blue and red codes are coded for clusters with low and high gas entropy. And I'll get into this a little bit later, but the blue are the so-called cool core clusters with low gas central entropies, and the red are the non-cool core clusters. And what you should notice is that, at least for these two indicators, whether it's a cool core or a non-cool core doesn't seem to matter. And one of the reasons for that is that the CE, so it's the X-ray temperature, and then sub CE, that's core Xi. So it's taking out the so-called cool core and just showing the temperature plotted here is the temperature outside of the core. You can see similar analyses by Adam Mance from 2016, and some people have attempted to extend these things to lower masses. I will point you to Catula et al. From 2015, who included group scales, clusters from the CCCP and Cosmos survey, and there's some work by Imetsu from the XMM XSL survey. These projects have weak lensing masses that probe that 10 to the 13 to the 10 to the 14 solar mass scales, but it's noisy, and so a lot of those works are often fitting just the normalization. They're assuming the same slope, and it's still very, very tough work. Okay, so I'm going to show you a couple of pretty pictures. This is the center of the Perseus cluster. The red is coding where the radio is. The pink, it's a little harder to see. That's H alpha filaments in that central galaxy, and the purple is where the X-rays are. And then my next picture is going to show you an edge-enhanced an X-ray image of the same region, where the smooth X-ray emission that's peaked on the central galaxy has been divided out, and you see an amazing amount of contrast that's in these in the X-ray gas. So you might wonder, well, how could we possibly call this hydrostatically in hydrostatic equilibrium? And so there is evidence for fluctuations. There is evidence for time-dependent impulses from the AGN coming from the central galaxies. But every piece of evidence, even for this cluster, shows that these fluctuations are subdominant in terms of providing pressure support to the gas. If I'll point you to work by Irina Zhurleva, who studied these fluctuations and was able to make estimates of, what the level of turbulence and so forth in the gas, and concluded that it was subdominant. And that was confirmed by the Hitomi observation in 2016. It was able to make an observation of the center of the Perseus cluster and resolve the X-ray emission lines, primarily of iron here, and showed that there was very low turbulence levels in the core. The Nature paper argues that this was, surprising and amazing, but I mean, people like Irina were predicting this, that the turbulence levels are consistent with the levels of fluctuations in the surface brightness mass, and so the conclusion is that the pressure profiles are consistent with being nearly hydrostatic in these cluster cores. Okay, so this is one example. It's a nearby example. We'd love to have more of these. The CRISM mission, which is the follow-on to the Hitomi mission, is under construction and underway. It will be able to look at a few more examples and possibly map even the Perseus cluster a little bit better. But Athena and later, hopefully, the Lynx mission will be able to do a much more comprehensive job of mapping out these cluster cores. So CRISM will have fairly low angular resolution compared to, say, Athena, and definitely lower spatial resolution than the Lynx mission will. So stay tuned, but this is the kind of data that Chandra and XMM, cannot provide, especially with CCD spectra. So this is for an X-ray astronomer who has studied spectroscopy since I was an undergrad. This is very, very exciting stuff. So we got a glimpse of our future in X-ray astronomy through the Hitomi observations. Okay, so we have some pretty good ideas of how much baryonic mass in the universe. I was claiming that clusters are pretty good fair samples. So from the Planck mission, there's good constraints on omega baryon and omega matter. We heard a bit about the constraints on where these baryons are from the fast radio burst from Macquart 2020. I had no idea he had passed away. What exciting work and what exciting science this young man was doing, and I have to say, I did not know, so I was taken aback. Okay. Anyway, so with the X-rays, we can measure the baryons in clusters. They light up in clusters, and on the right, I'm showing a compilation plot from Larry David. I believe this is 2014. I should have annotated that. I'll do that if I get a chance to repost the slides. But he compiled these measurements to compare his observations, which are in the red there. But the blue observations are for the groups, the F gas for groups. Those are from Ming Sun's work. And the open circles are for the gas fraction inside of R2500, which is below the filled circles, which is the gas fractions inside of R500. R500 is really difficult to measure out to for groups, so there's fewer of those points, but they're clearly higher than the gas fractions inside R2500. And the same sort of color code scheming, filled versus open, is plotted for the clusters. The dark points are from Vic Linen, and the green points are, I'm forgetting. But the point being is that the measurements at R2500 are sort of systematically lower than the measurements at R500. And as you include more and more of the cluster's virialized volume, the gas fraction also increases. And the distinction is bigger for groups than it is for clusters. And if you include in that baryon census the stars, on the cluster side of the mass scale, you pretty much account for the baryons in clusters. If you add up the gas and you add up the stars, that sum is very, very close to the baryonic fraction you'd expect cosmologically. Okay, so I've been spending a lot of my career thinking about the central galaxies and halos. And the central galaxies are, they're not, okay, not every cluster has a clearly identifiable central galaxy, but when they do, they're either this giant quiescent galaxy, old stars, not much cool gas, or they are an active central galaxy. And what I mean by active central galaxy is considerable evidence for cold molecular gas, hundreds of millions of solar masses, recent star formation. This star formation is not assembling that galaxy, but it's big in an absolute sense, sometimes up to 100 or more solar masses per year. So the galaxies that are forming the stars most rapidly in our local universe are some of these central galaxies in terms of their absolute star formation rates. And when you look at their normalized star formation rates, that is their star formation rate divided by their total stellar mass, they almost don't register as a star forming galaxy. They're fairly quiescent by that definition, but they look like this. That's because you're dividing, that 100 by a trillion solar masses. So anyway, so why are some of them on and some of them off? Seems to be directly associated with the thermodynamic state of the halo that they're embedded in. And we've known this in a way for many, many years. So here's a couple of example plots on the left. This is an X-ray surface brightness profile of two galaxies, galaxy clusters with very, very similar outer temperatures. There's what we call a cool core cluster, Abel 2390, and then I'm just comparing it to a well-studied non-cool core cluster, Abel 2219. The cool core clusters tend to host these active brightest cluster galaxies. The non-cool core cluster never hosts an active brightest cluster galaxy. So there's a stark dichotomy on the cluster scales, and it seems to be related to what their X-ray gas is doing. So the cool cores have a higher central density, higher central surface brightness. They also tend to be more prominent in X-ray selected samples. So if you're going out there and you're trying to find clusters of galaxies by their X-ray profiles, the cool cores stand out most prominently. Sometimes they're a little too prominent. I'll give you the example of the Phoenix cluster, which is the most luminous X-ray cluster in the universe that we know about. And it was not discovered in the X-rays because in the X-rays it was so bright and so peaky that it was classified as a point source in the Rosat All-Sky survey. And it took a Sanyaya Zeldovich survey, the South Pole Telescope, to find it and cross-identify it with a cluster of galaxies. So it's a little mud on our face as X-ray astronomers that the radio astronomers found it first. Anyway, so these things are called cool cores or non-cool cores based in part because they're typically in a cool core cluster, the central temperature declines. So this is what I'm showing over on the right is the cool core cluster temperature profile shows a decline in temperature into the center. This is not due to cooling. This is just due to the structure of the X-ray gas halo and its gravitational potential. So I want to eliminate that misconception right away. And you have the non-cool core cluster with a fairly constant temperature as a function of radius. And so when we compare their clusters for their characteristic temperature, it's been typical to, how much time do I have? Okay. Okay. I think I have 5 minutes. All right. Anyway, so I'll roll. So we can plot a luminosity temperature relation, and again, if you excise that central that central core, which is brighter and often a different temperature from the rest of the cluster, if you excise those cores, you get an LT relation that's a lot better behaved. So I've been spending too much time on clusters, so I want to extend that LT relation down to lower masses. And this is a plot showing a number of measurements of luminosity and temperature from clusters at the high mass, high temperature end of the scale to groups from Ming Sun et al. Those are the green plots. And I wanted to call your attention to an effort to stack X-ray data around luminous red galaxies. This is the Anderson et al. Work, and those are the purple. And that takes this LT relation down to very low temperatures and low masses. And it seems to show that the LT relation that applies to clusters extends over many orders of magnitude of luminosity down to low masses. Also on this plot, I'm showing the self-similar expectation, which is of much higher luminosity. But feedback works to reduce the density of that gas halo and suppress the luminosity. And it looks like a similar sort of an LT relation may apply over many decades of temperature and mass. Here are plots of halo gas densities. This was submitted in a white paper to the ASTRO 2020 survey. Galaxy clusters is on the left. That's from the accept sample. The blue are the cool core clusters. The red are the non-cool core clusters. The brown line shows you the cosmological expectation. And the purple line, the purple magenta dash line, shows the upper limit to the density that's set by the precipitation limit, which causes the gas to condense. If it gets any more dense than that, it's going to condense, and feedback will regulate it up to that purple line. So that's an envelope that limits how dense these clusters can be. And the combination of the cosmological limit and the precipitation limit gives you like a rule up against which the observed profiles seem to bump up against. So clusters are regulated, at least at large radii, at R500 greater than a tenth of R500 or so, by cosmological parameters, which is why they're more regular out there. Okay, and why excising their cores shows more regular relationships with mass and temperature, where inside that you have their upper mass density is regulated more by precipitation, which is the feedback balance. And as you move to lower mass systems, the cosmology limit is less relevant, and feedback is more and more important in determining the density profiles, and therefore the luminosity, how easy it would be able to see these things in emission as you go to lower and lower scales, all the way down to the Milky Way. And my last plot I'll show you here is all these things combined: clusters, upper left, groups, which wasn't shown in the previous slide. In the upper right, lower left, galaxy density profiles from X-ray observations from the Chandra archive from Babbitt et al. 2018, and an ensemble of constraints on the Milky Way halo compiled by Voigt et al. In 2019. The purple line that is on the bottom of each plot is a fit to the Anderson data from Singh in a paper that will be published in 2021. And you notice that it's lower than the density profiles for groups and galaxies. And it kind of runs through the middle of the clusters. So maybe the clusters are relatively representative, whereas in the galaxies, we're still probably seeing some of that Monquist and Eddington bias that I'd mentioned at the beginning of this talk. And I'll just close with this last closing thought slide. It's not really a summary slide. And that is thoughts, to take forward to this workshop and this meeting. One is that weak lensing masses are considered to be relatively unbiased. So if we can get weak lensing masses of galaxies, this is going to be great, but we need simulations of observations that connect the weak lensing expectations with what you'd expect from X-ray emission and UV absorption. Subaru and DECCAM measurements are pushing these weak lensing techniques to nearby local volumes. I'm involved in a new project that just got a lot of DECCAM time. These data sets are extraordinary. It's like 2 terabytes per cluster. I don't know how we're going to manage that. Anyway, but it's pushing these measurements to lower mass scales. And looking to the future, Euclid and Nancy Roman telescope are going to make extraordinary shear measurements and constraints at higher K, smaller mass structure. The gas halo is where most of the baryons reside. It's where the fuel for new stars and black hole growth ultimately originates. And if you look into past history, CGM is often relegated to a tiny little slice of the baryon budget, but I think we should be remaking those pie charts so that the CGM is properly represented, because I think it's important. And sometimes missions and observation follow-up is dictated by how relevant the science is. I think this workshop is going to show that the CGM science is super important and it's where most of the baryons are. So I think we need to rework some pie charts as maybe one of the outcomes of this workshop. And lastly, the physics of gaseous halos combined by a dark matter potential spans a huge range of mass scales from galaxies through clusters, and we can learn a lot if we can somehow pay attention across all these observations and all these simulations and all these different ways of coming at measuring these things and studying these things. It's really hard because the volume of work is amazing. But I think we have to take the effort to pay attention to cross-disciplinary progress. So that's my closing slide. And I think that was 45 minutes.
Thank you. I'll give you actually live applause. And if you, we will, I will be summoning people back 5 after the hour for the panel discussion. We'll give people a 12-minute break. I see questions are already going into the Slack channel. So there are already some questions there to think about, to address. Please keep putting your questions there. Megan will answer them throughout the day if necessary. And we'll be reconvening live for a discussion a little over 10 minutes from now, 5 after the hour. And I will thank the speaker again.